happy to welcome Ruchira. Am I pronouncing it Ruchira? She's going to tell us about scattering length and effective range corrections to unnuclear numbers. So, please.
Yeah, hi everyone, and thanks for organizing this conference and also for letting me talk about my work here. So, this is some work that I just finished with my PhD advisor Damson and Shubham, who's a postdoc at University of Chicago. So we were just trying to understand something called nonrelativistic conformal field theory, and more specifically apply it to certain kinds of static processes. So that's what I try to tell you about today. So to start off, let's consider some scattering process where you have, say, two particles A1 and A2 which come collide and then give you some particle B and a bunch of neutrons. What we are interested in calculating is the differential cross-section of this process, let's say with respect to the energy of particle B. And the question we ask is, how much information can we get about this differential cross-section without getting into the microscopic details of the reaction? So there's two hints that come to our rescue. The first is when we look at this energy regime. So if we fix some center of mass energy of A1 and A2 and then look at the energy spectrum of this product B, and then look at the end point of this, which is when the particle B will have the maximum kinetic energy. So in this regime, the neutrons will move very slowly with very low kinetic energy relative to each other. So in this energy regime, you can break down the scattering process into two parts. So the first is when A1 and A2 collide, and then the second part is this, where there is some interaction between the neutrons before they scatter off to free neutrons. So now when this sort of breakdown happens, you can actually break down the differential cross-section also into these two parts. So the first is that corresponds to the first step of the process, and then the second is this second part of the process, which is the decay into free neutrons. And then the second hint that helps us is to understand this decay process of the neutrons. So before the neutrons become free, they are interacting with each other, and we can understand that interaction by something that by just some natural properties of the neutrons. So neutrons by themselves present a natural realization of what is called fermions at unitarity. So fermions at unitarity is a non-relativistic model of spin half fermions with point-like interaction. So as such that their interaction can be fine-tuned to give you infinite scattering length. So it just turns out that there is no scale in this problem, and it turns out to be a non-relativistic CFT. So neutrons in a certain energy regime, which is given by the scattering length and interaction range, can be modeled well using this non-relativistic CFT. So if I now combine these two hints, which is first the breakdown of the differential cross-section into two parts, and then the second, which tells us about the interaction between the neutrons, it gives us this new picture called the unnucleus, which is that in a certain energy regime, we can model the interaction between neutrons as a field in a non-relativistic CFT. And taking motivation from George's idea of unparticle physics, Son likes to call it unnucleus physics. Now, the idea is that since it is a non-relativistic CFT, there are certain constraints placed on the two-point function, just like in usual CFTs. So then that then enters the formula for the differential cross-section, and it gives us this prediction, this power law behavior for the differential cross-section.
So what can you determine like what is delta ON?
Yeah, so delta ON corresponds to the scaling dimension of the primary operator. So for instance, if you have n neutrons in the n, then the object here is a charge n primary operator in the theorem. Now, like in CFTs, you have this state operator correspondence. There is a similar correspondence for non-relativistic CFTs as well. So that is one way to calculate the scaling dimension of these primary operators.
So in general, what's the condition to have state operator correspondence?
In general,
So in CFT, in non-relativistic CFT, so what's the when do we have state operator correspondence?
I mean specifically in non-relativistic or generally, how do we think that we can?
You know, for example, why is there state operator correspondence in non-relativistic?
The way I understand it is that there is a notion of these ladder operators. Basically, you can define primary operators, and then you have these ladders which take you and give you descendants. And you can have a similar analogy in a harmonic oscillator, where you have similar ladder operators. So, in that sense, you can draw the state operator correspondence. But I don't know of a general, like if you just gave me a theory and asked me if there would be a state operator correspondence, I don't know how one would figure it out. But for any non-relativistic CFT, if you place that problem into a harmonic well and then just solve the quantum mechanics problem, that would give you the scaling dimension of the quantum mechanics.
Here's Skelton.
Sorry?
Here's Skelton. The state that final zero.
But there is some weird version of conformals, like the conformal generator. That's right.
Yeah.
I think it's crucial. I think it's crucial. There's probably something
Yeah, so
going
that-
along what you said.
That forms one of these ladder operators.
Yeah.
that takes it up.
So what's the definition of non-relativistic?
I'll get to it. Yeah. I just motivating the physical problem that we are trying to solve. Yeah. So, so another thing, so this unnucleus picture was introduced by Saul and Hammer in 2021. What we were interested in doing further was to account for corrections that come from a finite scattering length and a finite interaction range. Because the neutrons in reality do have a finite scattering length and a finite interaction range. So the way we do that is that now we are at a non-trivial fixed point. So we would like to do some sort of conformal perturbation theory kind of thing around it. So we capture the effects of these corrections in terms of relevant and irrelevant terms in the Lagrangian, and then do some conformal perturbation theory. So these would be the original undeformed correlators, and then these are the corrected deformations that we calculate. So we just work up to first order corrections. So just to flash some results. So it turns out that the correction from scattering length goes as 1 by square root omega, where omega would be the energy difference, E naught minus E. And the correction from interaction range should go like this. Now these formulae are just predicted from the fact that we have Galilean invariance in the problem. There is no explicit calculation needed for this prediction. But to calculate these specific constants like C and C prime, one has to do more explicit calculations, and that's what we do. So we work in the specific case where 3 neutrons are emitted. So we would be looking at something like a charge 3 operator in this non-relativistic CFT. And hopefully by the end of the talk, I will be able to make it clear why it is not trivial to think about more like any general charge and operator. And something surprising that we find is that C prime is just 0. So this is the contribution from the irrelevant deformation in the CFT, and it turns out that the finite piece always vanishes in integer dimensions.
Somebody's question is R0 large or small?
R0 is like 2.74 meters, so it's a small
It's
number.
pretty small.
Yes, relative to the scattering length, which is around 24 meters.
Good. So if C prime had not vanished, that term would still be a small correction.
Yes, yes. Yeah. The surprising part is that it is exactly 0 in integer dimensions, and that's what we don't understand. So yeah, now for the rest of the talk, I will just introduce what a non-relativistic CFT is, and specifically this model of fermions and unitarity that we work with. And then I will talk briefly about how one goes about calculating these first correlators and then their corrections. So let's first just start with the free Schrodinger equation. It turns out that the largest symmetry group that this equation has consists of the usual Galilean transformations, phase rotations, and then it also has scale invariance and conformal invariance. And all these transformations together form what is called the Schrodinger group. And it's not just the free Schrodinger equation that has this symmetry group, but then there are also other examples. For instance, if you had a 1 by r squared interaction, or this example of fermions at unitarity.
So if I transform your composite, is it still a non-relativistic?
I'll mention that in the end. There is something non-trivial about it, which has to do with something called the FMO effect, but I'll mention that. So, so a non-relativistic CFT then is just any non-relativistic, any QFT with Schrodinger symmetry. So now, like in usual CFTs, you also have a notion of primary operators here, which is defined with respect to the generator of boosts and conformal transformation. And like in usual CFTs, the 2-point function gets constrained up to an overall constant rho. So here, delta O or N, so delta O is the scaling dimension of this primary operator, and NO is the particle number. So just to mention, but like in usual CFTs, so the 2-point function gets constrained, but the 3-point function is not constrained, and so there's very little hope for the 4-point function.
I have a question. Only it has a dimension 1. Otherwise, in the exponent, x squared and t is dimension 4.
No, so since this is non-relativistic, x and t scale differently.
Ah, sorry. Yeah. No.
So, sorry? No, it comes with everything. Because, as in, you're asking, so N0 commutes with all the generators, it's like a central extension. And when we try to constrain the 2-point function based on whether, so if you just take any 2-point function or any correlation function and then try to impose the fact that you indeed have this scale invariance, Galilean invariance, and conformal invariance, then and then you have number conservation, so that gives you this n-order exponential.
Get rid of E and K. So this part of the
Sorry?
right? Your E and K, the commutator is N. And
Huh.
so they don't E and K.
Yes. Yeah. Yes, that's the case. Yeah. So now let's look at a specific example of fermions at unitarity. So physically, the way you can think of it is that you have a system of spin-half fermions with point-like interaction, and I'm fine-tuning the interaction strength to be at a non-trivial fixed point. This non-trivial fixed point is where the scattering length becomes infinite. Another way to think about it is that you have particle in a box, and you're fine-tuning the depth and the width of the potential such that you have just one bound state which is at 0 energy. So, yes. Yeah.
By the way, I always confuse, like, why do people call this fermion and unitarity? Because it kind of
Because it's actually the unitarity bound when you calculate the S matrix.
and unitarity bound. I see.
So, yes. So now this is just a Lagrangian for fermions with point-like interaction. I just introduce Hubble-Stratton-Lorentz field D, and then I fine-tune this C. So what one would do here is calculate the dimer propagator. So this D is what I call the dimer. So calculate the dimer propagator and then fine tune C such that it always cancels the huge divergence. And when I take A to be infinity, that's when we are at unitarity at this non-trivial fixed point. So once we are at this fixed point, we can add perturbations to it and start accounting for a finite scattering length and a finite interaction range. So a finite scattering length would take us to lower energies towards the free fixed point, and its effect can be accounted through relevant operators. It turns out that the only relevant operator that one can add is this d dagger d, and to account for effects of finite interaction range, we can add a bunch of irrelevant operators. At the lowest dimension irrelevant operator that one can add is this, and above this there would be a tower of like infinite number of irrelevant operators.
Explain why this LCF takes as a short person.
So one way to see it would be to look at the propagator, which is the dimer propagator, and we see that when we take A to be infinity, there's no other scale left in the problem, and then you can transform it back to the position space and see that the propagator is exactly what one expects from a non-relativistic CFT. But that's just one quick way of seeing it. Another way to see it is to actually couple it to some kind. So one is that you just transform everything and see. Another way is to couple the theory to background gauge fields and metric, and then see that it indeed has satisfied this whole big set of coordinate transformations. So I can give you some. There is a paper, 2005 paper by Swan and Woodgate, where they explicitly show that this theory of fermions and unitarity is indeed a non-relativistic theory.
This theory is star with some number independently irregular.
Coming from a scalar whose magnitude mass is so scalar that's also the fixed point. What's
This theory is an actual.
Oh, yeah.
Obviously, it's some limited term.
So generally the way I would have seen if anything has a symmetry would be one to look at the action and then take see if it is indeed invariant under all the transformation. And the other would be to look at the correlation functions, and we see that in those there's no scale left.
So, is it clear? Regarding the last condition, is it clear that the coefficient regional of the outcome should be R0? I'm basically asking why does this condition capture the impression of R0?
Because those are the only two effects that we are trying to capture, and R0 starts to become important when we go at higher dimensions.
But can you refer Schoenberg's theory? Does not R0 refer Schoenberg's theory?
Yes, because then you're saying that the interaction is not a delta function interaction, but it's indeed some kind of like you're adding a scale to the problem, so you're taking scale variables.
Maybe another point. So in the last condition, there are really two terms. There's the BT and there's the gradient.
Well, that's to preserve Galilean invariance. Galilean invariance. We want Galilean invariance to stay in the part.
So the range finite the finite A is relevant.
Yes.
Finite are not relevant.
Is it the leading irrelevant perturbation?
Yes, because you have like the lowest order you just have one term that you can add, then just so now like after we have the full Lagrangian, the next step is to calculate these 2-point functions. And the very first thing that one has to do is to define what these primary operators are, because all I've said is just set up how the Lagrangian looks like, but I have not defined what these primary operators are. These, more specifically, these operators that would correspond to the like that would then decay into n neutrons. So something like a charge n operator. So the way we would define these unnucleus ON operators would be through their matrix elements. So for that one would have to know the Hilbert space, which would be the Hilbert space of n fermions at unitarity. Now once we have defined the operator, we can go on to calculating the two-point function. The nice thing that happens in a non-relativistic system is that there's particle number conservation, which means that I can insert a complete set of states, but the only states that would click would be these n body states. So then once I have this definition, I can just get the two-point function. Similarly, the calculation of the four-point function can be broken down to calculating these three-point functions, which again would rely on the calculation of defining these matrix elements. So let's look at how the Hilbert space for fermions at unitarity looks like. It turns out that you can model this problem in a quantum mechanical way using a boundary condition. So you take the usual like free Hamiltonian, so just the sum of kinetic energies, and then impose a boundary condition on the wave function, something as known as the Bethe-Fiols boundary condition. And more specifically, we are saying that when two fermions come together or come close, the wave function should have this kind of behavior where it goes as 1 by r the distance between the two fermions and then a regular piece. And more specifically, when you take a to be infinity, that's the unitarity limit. So now, once we have, so basically the Hilbert space would then consist of all wave functions which solve the free Schrodinger equation with the boundary condition imposed. Now a knife, once we have that, we can start defining our operators. And a knife definition for the operator would have been to just take the nth power of these psi or free fermion operators. But it turns out that because we have this non-trivial boundary condition on the wave function, that leads to divergences, and so the operators are not well defined. So to look at an example, we could consider a charge 2 operator and then just define it as something psi squared. When we start calculating its matrix elements, we see that because of the Bethe-Fiols boundary condition, it diverges as the distance between the two fermions goes to 0. So a more careful definition of the charge 2 operator would be to multiply it by this r and define it in this particular manner. Now similarly, as I mentioned, our problem was to solve the case for 3 fermions or where 3 neutrons are released. So that means that we first solve the problem of 3 fermions at unitarity. It turns out that it's not as easy to solve a 3-body problem. So, but then we have hints from Efimov's work. And to solve the 3-body problem, it's easier to introduce a certain set of coordinates that are called Jacobi coordinates. And once you have solved the problem, it turns out that the wave functions are labeled by these 4 eigenvalues. So there's the usual energy eigenvalue, angular momentum eigenvalue, and something new called the S value. Now, since we have all of these eigenvalues, we can define an infinite number of charge 3 operators which are labeled by all these different values. So you have the angular momentum label and the S label. So this will depend on the details of how the wave function looks like, and it has a slightly more complicated form. But an easier way to see how the rough form of a 3-body operator would be is to look at the L equals 0 case, which is the S wave charge 3 operator, and it has this simple form in terms of the charge 2 and the free fermion operator. And as you can see, it depends on this value S that one gets from solving the fermions at unitarity problem. So once we have defined our 3-body operators, we can move on to calculating the correlators in the ways I described by just if they're all real numbers, real positive numbers for fermions, but for bosons they start becoming so that's the number. So for bosons they can become imaginary, and so the scale invariance from continuous scale invariance it breaks down to discrete scale invariance. And fermions is positive and real, yes. No, they are discrete S values. Yes. No, it's a. I have the values written down somewhere, but they're not nice rational numbers. So, yeah. come through solving a differential equation, the equation is so yeah. So then we can calculate these correlators. So the undeformed correlator would have been predicted by the form that we had, and we see that it depends on these values of S. And then we can calculate the relevant part, the contribution to the relevant part, which is the A correction. And then we can also calculate the contribution to the irrelevant operator. Now it turns out that so what we are essentially calculating are 4-point functions of this form. And when we start calculating the irrelevant operator, it have a divergent piece, which just means that that O3 gets renormalized. But then there is a finite piece, which we observe always goes to 0 whenever we are in integer dimensions. And that is some effect that's also seen in usual CFTs when one tries to calculate the contribution of irrelevant operators. We didn't find a very nice explanation for why that happens apart from the fact that it happens. So it would be nice to understand why that is. So since you asked, so these are just some numerical values because there is either some experimental data or there's people who've done like more microscopic calculations which give us these values. So in principle we can also compare what our predictions are or what the unnuclear predictions are with some kind of data. So these are just some numerical values that we can.
So what is S in terms of some data in probably some decay theory?
So yeah, I'm not sure what it would correspond to a more microscopic problem, but it's just some parameter for a free body problem. That's how I would think about it.
Can just solve the body problem for local life.
Yes, that's exactly what we do. Yes. So, just to summarize what we've done, it turns out that if we were interested in studying specific scattering processes when neutrons are released, and we simplified the problem by mapping it to a non-relativistic CFT. Now, what we had to do then to calculate these correlation functions was to first define these operators, and the way we defined it involved solving the problem of fermions at unitarity, so n fermions at unitarity. So it turns out that, so then it seems like the only requirement that one would need to keep predicting these values for any scattering process with n neutrons would be to solve the problem of n fermions at unitarity. But there are no analytical solutions for more than 3 neutrons, which is why we have very nice expression for 3 neutrons, but more than that we don't have any control over it. So it would be nice to either go in the large n limit and do something, or find a better way of this whole thing. So what more could be done in this regard to just like finish things off? One would be that we sum up all the relevant perturbations, and that would mean that we go from this non-trivial fixed point to the free fixed point, where the neutrons are now decaying into free neutrons. And that would then in a way help us understand how this process actually happens. So when neutrons are interacting and then they become free. Another thing that we would like to do is to understand why this first order R naught correction vanishes, why the finite piece is 0 in integer dimensions. And just to come back to the point of bosons, so it would be interesting to see if there is a notion of unmolecular physics, which is to study, instead of looking at fermions, look at bosons. Now, something interesting that happens in the case of bosons is that you cannot have 3 bosons at the same point. And so that means that you have to introduce a regulator in your problem to make sure that that doesn't happen. And so that leads to something called the FMO effect, where the energy scales now form a geometric series. So in a sense, it is like the breakdown of continuous scale invariance to discrete scale invariance. So that was something that I tried exploring for a while, but I don't know of any chemical reactions or any reactions where you can model them as bosons and then see this effect in the elements. So yes, that's all.
Thanks for keeping to time. Questions?
Yeah, is there any quantum systems that also described as a non-relativistic CFT? Because quantum systems, most of them, they are not apparently relativistic in the IR.
Yeah, so for instance, cold atoms, they are often modeled as fermions at
Cold
root
atom.
Yes. So they you can fine tune like in experiments, you can fine tune the magnetic field such that the scattering length is infinite. And people often, in fact, study the ephemeral effect also in that.
I see. So is there any quantum lattice system that's also described by this non-relativistic CFT?
Not sure because so then in fact if you can somehow that would be a if you had something like a 1 by r squared interaction, then that would be a long range interaction. That also has this virtual interval symmetry.
Okay, thanks.
So with relativistic conformal symmetry, something special and interesting happens in two space-time dimensions. Is there something similar with non-relativistic conformal filter where there's some magical space-time dimension with extra
I think there's something in one dimension that it is exactly like the CFT.
One spatial.
One spatial dimension or one?
Yeah.
Yes,
One
one
spatial.
spatial dimension.
Okay.
Yeah, but I'm not sure. I don't know. I'll check that.
Can you tell us a bit about the n-totality limit that you mentioned? Can you calculate this delta in that limit?
No, we're not sure. So the people do look at these like non-relativistic CFTs in the large n limit. That's not something that I've looked at. But then the hope would be to use that, like introduce a finite chemical potential of the problem, and then define these operators and something. So I think people like Simeon and others have worked with.
So like the one that if this scattering process not be done like in the way that normal nuclear physics people would do. I mean, for some reason I thought that it was all been done since I don't know before I was born. But so isn't that all the technology in doing nuclear scattering cannot capture this scattering process?
So you're asking if these predictions could have been made without using this formalism?
I guess so, yeah.
Yeah, so I think what I know is that generally people use very specific, like reaction specific or like microscopic calculations to do it. So they try to model the potential between these neutrons in a certain way and then do the calculations. The reason this is nice is because you're not using any of that information. Basically, the only information that you're using is the number of neutrons that are released in the n. And then we only say data that goes is the scattering length of the neutrons, which we know is universal, and the interaction range, which also we know.
This is much better than the traditional nuclear physics way of doing it. Because you can do controlled errors and everything, like it's an honest computation, as opposed to the traditional approaches of nuclear physics.
Well, it's a regime where microscopics doesn't matter.
Right? That's nice. That's very nice, yeah. The traditional way of doing it is
You can't apply it for everything. You can apply it only for some.
nobody promises this.
But
You can always do the slice thing, but the fact that you can
It's a
big deals.
universal process.
but then we have like try to account for corrections and go a bit higher with the energy regime. Yeah, we can't apply it.
I was confused with your comment that bosons cannot be a
No, so what I was trying to say here was that the wave function, so more simply, when we are solving the problem of three bosons at unitarity, you need to make sure that the wave function does not die, like it's normalizable. And for fermions, because of poly spin statistic, that is not an issue, but then for bosons, you have to put it by hand, like introduce a regulator, and that leads to these S values being complex and
Does that basically mean that bosons at unitarity are this preferred phase? Is that what this means? Or you said that the critical part doesn't exist. Is that correct?
so here we don't even have any chemical potential or anything, so this is like very, it's not dense, yeah.
Yeah, sure, but it sounds like there's instability because of this imaginary is that
Yes,
not right?
yes.
Okay.
Yeah.
And that instability coupling will break the U1 particle number symmetry. Is that correct? Well, I was assuming it meant that the whole theory was bad, that there was an operator with imaginary dimension. Maybe that's not.
No, so we just, I was just referring to a simple three-body
Right,
problem
okay.
where that happens.
Right. Okay. So that doesn't stick in the whole theory. You're saying that the theory is okay, just this operator is bad. Is that right?
Yes, that's the reference.
So for two-body case for bosons, it would be like we wouldn't run into